Namaste friends, I welcome all of you in this session. Today we are going to learn about single electrode potential, or it is simply known as electrode potential, types of single electrode potential, that is oxidation electrode potential, reduction electrode potential, or oxidation potential or reduction potential, then how to determine or measure single electrode potential. Then what are the reference electrode which are used to measure single electrode potential, and Nernst equation to find out single electrode potential and that. Okay, so let us start. In previous lecture we have seen what is meant by electrode potential or what is meant by a potential. Okay, we are aware that whenever an metal electrode is deep in its ionic solution, then potential is developed or electrical double layer is formed. Okay, for example, I will show you this diagram. So formation of electrical double layer, it means nothing but the potential. So here the metal rod of cadmium, when deep in its ionic solution, cadmium sulfate solution, so this solution contain cadmium ion, then the cadmium atoms at the surface have tendency to go into the solution, leaving behind the electrons. Okay, so due to this the metal rod or electrode becomes negatively charged. Okay, this negative charge or potential is developed because of oxidation reaction, hence the potential is called as oxidation potential. Here in this case the silver metal is deep in its silver ionic solution, so the silver ions from the solution have tendency to deposit on the metal electrodes and leaving behind the negative charge. So this process is called as the reduction, and the potential developed is called as the reduction potential. Okay, so simply we can say that a single electrode potential is the potential developed when a metal electrode is deep in its ionic solution. Okay, or simply we can define as the single electrode potential or half cell potential is the difference of potential between the metal and the solution around it at equilibrium. So this word is very important. Okay, so the potential is single electrode potential is the difference of potential between the metal and the solution around it at equilibrium, or simply in simple language we can say that it is the potential developed when a metal electrode is deep in its ionic solution at equilibrium. Single electrode potential depends on these four things. First thing, nature of the metal. Okay, nature of metal, whether it is monovalent, bivalent, trivalent, etc. Concentration or activity of ions in the solutions. Third, temperature, and last one is the pressure in case of the gas. This single electrode potential is of two types: oxidation potential and the reduction potential. Okay, so yes, I have explained you. Oxidation potential means it is a single electrode potential which is developed due to oxidation reaction is called as oxidation, and if it is developed due to reduction reaction, then it is called as the reduction potential. Now question arises in our mind, how to measure single electrode potential. So to understand this, let us revise some basics. Now look at here the methods to measure single electrode potential. Okay, so now in order to measure the single electrode potential, individual potential, we need a reference electrode. It is not possible to determine exact values or absolute values of single electrode potential. Now how it is measured? Okay, so this single electrode is combined or coupled with the referent electrodes, with a reference electrode. As we know, when we connect two half cells, then an electrochemical cell is formed, and the potential of an electrochemical cell is given by sum of potential of left hand electrode and right hand electrode. That is, At the left hand side oxidation takes place, so potential will be E oxidation. At right hand side reduction takes place, therefore potential will be E reduction. Now look at here, the electrode whose potential you want to determine is coupled with the reference electrode. Here SHE stands for the standard hydrogen electrode, or it is if it is not available, then calomel electrode is used, saturated calomel electrode. So the E electrode plus E saturated hydrogen standard hydrogen electrode, and this standard hydrogen electrode have a potential of 0. Okay, so this equation can be rearranged. Therefore the potential of electrode will be equal to the potential of an electrochemical cell or EMF of the cell. Thus the single electrode potential of the given electrode is itself the EMF of the cell, which is formed when the electrode is coupled with standard hydrogen electrode or when it is coupled with a reference electrode, that you can say. Okay, तर कुठल्याही सिंगल इलेक्ट्रोडचं पोटेन्शियल कसं काढलं जातं? ओके, तर त्या इलेक्ट्रोडला रेफरन्स इलेक्ट्रोड सोबत कंबाईन करून म्हणजे त्याचा इलेक्ट्रोकेमिकल सेल तयार करून त्या सेलचं पोटेन्शियल काढलं जातं आणि त्या सेलचं पोटेन्शियल इज नथिंग बट द पोटेन्शियल ऑफ सिंगल इलेक्ट्रोड. ठीक आहे, सिंगल इलेक्ट्रोडचं पोटेन्शियल प्रॅक्टिकली डिटरमाइन करणं अशक्य असतं, म्हणून त्याला रेफरन्स इलेक्ट्रोड सोबत जोडूनच आपण त्याचं पोटेन्शियल मोजू शकतो. मग असा रेफरन्स इलेक्ट्रोड निवडा की ज्याचं पोटेन्शियल 0 असेल किंवा सर्टन फिक्स व्हॅल्यू त्याला असेल. ओके, नाव देर आर 2 रेफरन्स इलेक्ट्रोड यूज इन दिस potentiometry to measure single electrode potential. Now look at here. Yes, the screen is visible now. So the reference electrode or standard electrode means what? The electrode whose potential is accurately known is called as standard electrode or reference electrode. The electrode whose potential is exactly known is known as reference or standard electrode. There are 2 types of reference electrode: primary reference electrode and secondary reference electrode. Standard hydrogen electrode is an example of primary reference electrode. Saturated calomel electrode is an example of secondary reference electrode. Now look at the diagram of primary reference electrode. This is the primary reference electrode. Example, standard hydrogen electrode. Okay, now look at this diagram. So this is the platinum foil, the black one, platinized platinum foil. It means that platinum is adsorbed on this platinum foil. Due to this, the plate become black colored. Now this platinized platinum foil is connected through a copper wire, and this copper wire is further connected to the another half cell, or it is connected to the potentiometer circuit. Now this platinum foil is enclosed in a glass chamber, and in this glass chamber a hydrogen gas with unit pressure, okay, 1 atmospheric pressure is here bubbled. Okay, so this gas comes from this inlet, this goes here and it is bubbled around this platinized platinum foil. Excess gas is removed from this outlet. This saturated hydrogen electrode is connected to another half cell via salt bridge. So this is the salt bridge. Now look at the cell representation. This is the gas electrode, so a metal support is used. So it is shown, this is the platinum is in contact with hydrogen gas is bubbled, and this electrode is deep in its ionic solution, that is the hydrogen ion solution. So this solution is of 1 molar concentration. Okay, so activity of hydrogen ion here is the 1 molar or unit activity. The EMF or the potential of this hydrogen electrode is equal to 0. It is considered as a 0 by convention. Okay, this is the diagram. Now from this negative sign, or it shows that this is the oxidation electrode. So oxidation of hydrogen gas takes place. So 1/2 H2 will give rise to hydrogen ion plus electrons. Now What are the drawbacks of this standard hydrogen electrode? There are 4 drawbacks. First drawback is it is difficult to set up this electrode. It is difficult to set up standard hydrogen electrode. Second drawback is it is difficult to maintain unit activity of hydrogen ion solution. Second drawback, it is difficult to maintain unit activity of hydrogen ion solution. Third difficulty is it is difficult to maintain unit pressure of hydrogen gas. It is difficult to maintain unit pressure of hydrogen gas. And fourth thing, there is chances of there is chances of adsorption of impurities over the platinized platinum foil. Okay, so these are the 4 drawbacks. First, difficult to set up this electrode in the laboratory. Second, difficult to maintain unit activity of hydrogen ion. Difficult to maintain unit pressure of hydrogen gas. And fourth, adsorption of impurities over the platinized platinum foil. So these are the 4 major difficulties. So in order to overcome this difficulty, we need to design a new electrode, reference electrode, called as saturated calomel electrode. Now look at this saturated calomel electrode. So this is a diagram of saturated calomel electrode. Now it is a secondary reference electrode, and why this is widely used in the laboratories? Because it is very stable and it gives reversible results. Okay, now look at this diagram of a calomel electrode. It consists of a big glass chamber, and this is a U-shaped glass tube is connected to this glass chamber or glass tube. Okay, vertical glass tube. Now this is filled with the mercury, and a copper wire is inserted, and this is connected to the potentiometer, further potentiometer. So this mercury is in contact with the inner solution of this glass tube and via platinum wire. Above this mercury, paste of mercury and mercurous chloride. This is called as calomel. MCQ can be asked. The calomel is shown by so and so. So mercury and mercurous chloride. Above this KCl solution is filled. This is the KCl solution. Okay, now this KCl solution is of 3 types: 1 normal, 0.1 normal, and saturated calomel. Okay, saturated KCl. So depending upon this, there are 3 types of calomel electrodes. Okay, so this is the overall diagram of the calomel electrode. Now what is the reaction taking place on this calomel electrode? So look at this. So this mercurous chloride undergoes reduction and it produces mercury and 2 molecules of chloride ion. So this is the reduction reaction going on here. Now what are the types? So there are 3 types. Look at here: electrode, symbol of electrode, and potential, standard potential. Okay, so 0.1 normal calomel means 0.1 normal KCl solution will gives rise to 0.3338 volt of the potential. 1 normal calomel will give rise to 0.28 reduction potential, and saturated calomel, that is saturated KCl solution, will give rise to 0.241 volt reduction potential. So these are the 3 potential. So by using this secondary reference electrode, we can measure the single electrode potential. How to measure? You just form electrochemical cell with this reference electrode. Okay, so you connect a single electrode half cell to the one of this reference electrode, and from this you can calculate the potential of given single electrodes. Okay, now let us discuss further. Okay, so what is the Nernst equation? How to find out the potential, single electrode potential? Okay, now look at this diagram. Now look at this reaction. So this is the general reaction, oxidation reaction, where the metal M is undergoing oxidation, producing metal ion and electron. Now you observe carefully here, this metal is undergoing oxidation, and this metal, if we consider reverse reaction, it will undergoes the reduction reaction. So this M is called as the reductant. It reduces others and undergoes oxidation. This Mn plus is called as oxidant. Okay, it oxidizes other and undergoes reduction. Okay, so you might be aware of these terms. So Nernst equation Okay, what is Nernst equation? This is the equation given by the Nernst scientist to measure the single electrode potential, which is equal to, now this is the oxidation reaction, so the EMF of the cell E oxidation potential is equal to standard oxidation potential. 0 means standard oxidation potential minus RT upon NF log of concentration of product divided by concentration of the reactant. Now these reactants are in a natural state, therefore its activity is considered to be 1. Here product, you need to consider only this metal ion. So next step will be, in simple we can say that, look at here, therefore oxidation potential is equal to standard oxidation potential minus RT upon NF log of, yes, activity of the product divided by activity of reactant. So reactants are in natural state, so option 1 is there. So I have replaced that by 1. Now in this equation, this E0 ox stand for the standard, okay, 0 at the top correspond to the standard, E ox means oxidation potential, E reduction means E reduction potential, standard reduction potential, R stand for the molar gas constant, T stands for the absolute temperature of the electrode system, F stands for the Faraday constant, N stands for the number of electron involved in oxidation or reduction process. A stands for the activity. Now look at the second reaction. This is the reduction reaction. Mn plus n electron gives rise to M. Okay. So the Nernst equation will be E reduction equal to E0 reduction minus RT upon NF ln activity of product divided by activity of reactants. So 1 upon activity of metal ion. Okay. Now this M is a reductant. It is reducing this metal ion, and this metal ion is an oxidant because, sorry, I just this is the reductant and this is the oxidant. Oxidant oxidizes other and undergoes reduction itself. Okay. Now let us go further. So in general, we can write the Nernst equation as, for oxidation reaction, the oxidation potential is equal to E0 ox means standard oxidation potential minus RT upon NF log of activity of oxidant divided by activity of reductant, and similarly for reduction, activity of reductant divided by activity of oxidant. Okay. Now let us consider more about the standard potential, standard oxidation potential and standard reduction potentials. Now look at this diagram, sorry, look at this paragraph. Let us discuss standard oxidation potential or standard electrode potential. आता स्टँडर्ड शब्द म्हणजे काय? ज्यावेळेस हा स्टँडर्ड शब्द येतो त्यावेळेस तुम्ही ॲक्टिव्हिटी, ही जी सोल्युशनची ॲक्टिव्हिटी असते ही ऑलवेज 1 असते असं कन्सिडर करायचं. ज्यावेळेस ॲक्टिव्हिटी 1 ठेवली जाते आणि पोटेन्शियल मेजर केलं जातं तर ते पोटेन्शियल नेहमी स्टँडर्ड पोटेन्शियल असतं. ओके. नाव डेफिनेशन ऑफ स्टँडर्ड पोटेन्शियल इज, so this potential represent the potential of the electrode when activity of its ion in the solution in which the metal is immersed म्हणजे deep, is unity. Okay. So standard electrode potential is nothing but the potential developed when an electrode is deep in its ionic solution having unit activity. This standard potential is of two types: standard oxidation potential and standard reduction potential. This oxidation potential, standard potential, is represented by word E0 ox, and reduction potential is represented by the word E0 reduction. Okay. Now definition: if the potential is developed due to oxidation reaction, then it is called as E0 ox, standard oxidation potential. Simple definition I have written here. It is the potential generated due to oxidation process when a metal rod or metal electrode is deep in its ionic solution having unit concentration. For this definition, only replace the word oxidation by reduction. So standard reduction potential is the potential generated due to reduction process when a metal rod is deep in its ionic solution having unit concentration. Okay. Now, now this is the very important things to understand. The standard oxidation potential is equal to opposite in sign to the standard reduction potential. म्हणजे काय, कुठल्याही सेलचं जे काही ऑक्सिडेशन पोटेन्शियल आहे तेवढंच त्या सेलचं रिडक्शन पोटेन्शियल असतं, बट विथ निगेटिव्ह साइन. फॉर एक्झाम्पल, E0 ऑक्सिडेशन विल ऑलवेज इक्वल टू मायनस E0 रिडक्शन, and E0 reduction will always equal to minus E0 oxidation. Now let us apply the Nernst equation for an electrochemical cell. So let us consider, this is the example of a Daniell cell. Okay, so zinc electrode is deep in its zinc ionic solution, copper electrode is deep in its copper ion solution. So this is the one half cell and this is the another half cell, left half cell or right half cell, and both the half cells are connected by a salt bridge. This double vertical line shows the salt bridge. Now on this is the left, right, oxidation, reduction, anode, cathode, oxidation potential, reduction potential. ओके, अल्फाबेटिकली ABCDच्या ऑर्डरनी हे सर्व गोष्टी आहेत, हे तुम्ही लिहून ठेवा कुठेतरी नंतर. आता हा जो ॲनोड आहे, ओके, याच्यावरती ऑक्सिडेशन होतं. सो रिॲक्शन विल बी झिंक विल गिव्स राइज टू zinc ion plus 2 electron. So n value is 2. Therefore, according to the Nernst equation, the oxidation potential will be E ox zinc is equal to E0 ox standard oxidation potential of zinc minus RT upon NF. N is equal to 2. Okay, log of activity of product upon activity of reactant. Activity of reactant is 1. Okay, so this is the equation 1. Similarly, this copper will undergo reduction. Reduction reaction is written. So the Nernst equation for this reduction reaction will be E reduction potential of copper equal to E0 reduction of copper minus RT upon 2F log of activity of product divided by activity of reactant. Okay, now both are the half cells connected to via salt bridge. So total EMF of the cell will be sum of EMF of two half cells. So ELHE plus ERHE. ELHE is my E oxidation, ERHE is my E reduction. So therefore E cell is equal to E ox plus E reduction. Now you add this value of E ox and E reduction, just we have calculate here. E ox is equal to this much, E reduction is equal to this much. Put this in this equation, then we get this equation. So E0 oxidation, this is the value of E0 oxidation. E reduction, this is the value of E reduction. Okay, now take the potential common and this RT upon 2F into log term to the other side. So we get E0 ox plus E0 reduction minus RT upon 2F ln activity of zinc divided by activity of copper. Okay, you will understand how I did it. So this E0 ox plus E0 reduction is nothing but the standard cell potential. Okay, E0 cell minus RT upon 2F ln activity of product upon activity of the reactant, right? So this is the E cell standard, E cell means potential of the electrochemical cell, right? Now this both this reaction number, look at yes, zinc oxidation reaction and reduction reaction. I will write this reaction again. So zinc will give rise to here for the simple understanding, Zn 2 plus 2 electron, copper 2 plus 2 electron gives rise to Cu. Okay, overall reaction will be Zn plus Cu2 plus will give rise to Zn2 plus copper. So activity is 1, activity is 1. For copper the activity is activity of copper 2 plus, and here activity of Zn 2 plus. So log of concentration of product, activity of zinc, and concentration of reactant, activity of copper. So in this way, simple way, you will remember this. Now this is the last topic of this session. So this is the general electrochemical cell reaction, a general electrochemical cell reaction. Then for this cell reaction, the Nernst equation will be, therefore the EMF of cell will be E0 of cell, standard cell potential, minus RT upon 2F into log of activity of product divided by activity of reactant. This is the Nernst equation for cell potential. Okay. So in next lecture, we will see how to calculate the EMF of a given cell. Okay, we will discuss the problems on it, and then with the help of problem, we will understand these different rules. So simple rules are there, not to worry much about this, and we will see these problems in the next lectures. So if you have any difficulty, then please free to ask your doubts or question on WhatsApp, or you can directly call me. So thank you for watching this session. Thank you.